to chair this morning session. So there will be two courses. The first speaker, Monique Laurent, unfortunately could not make it physically to Hagia Sophia Antipolis, but she was kind enough to make the arrangements so that the course can be given online. So Monique is with us online. And so there is a mic which is next to the computer. So if you have questions, either you go next to the computer and ask, or you speak aloud and I'll try to reformulate the question to Monique. I will be sitting here, so don't hesitate to ask questions. Yes? Oh, there is feedback there. Okay. So this, I should ask our expert, sound expert.
I don't know if it was the mic, but
there is indeed some background noise here.
So Didier, should I start? I somehow don't.
Yeah, there's some background sound, but
no, this is from the sound.
Yes, so unfortunately we cannot really do anything about it.
We can make it slower.
Okay. Okay. Good. So Monique, so you have an hour and a half for this first part of your course on semi-definite approximations for polynomial optimization with applications to quantum information. And the floor is yours.
Okay, thanks a lot, Didier. So good morning, everybody. I'm indeed sorry not to be there. I heard a few lectures yesterday and it seems to be really very nice. So I hope you enjoy the week. So indeed, in this mini course, I want to discuss how to design semi-definite approximations for polynomial optimization. And there will be a focus to a few selected applications to quantum information. So let's, this is a plan. So today I want to discuss what I call here into quotes, classical polynomial optimization. This is just optimization of polynomials in scalar variables, how to build SDP relaxations using sums of squares and moments. And I will discuss the application to detecting quantum entanglement in quantum information. And tomorrow we will move to polynomial optimization in non-commutative variables and how this models problems arising dealing with questions like maximum violation of Bell inequalities or entangled values of non-local games. So today variables are classical, scalar, and tomorrow variables will be non-commutative. So this, my lecture today will be rather basic. I will just very slowly go into what is polynomial optimization and what are the main techniques to tackle polynomial optimization problems in the first hour. So here is the setting. We have a polynomial function p, which we want to minimize over a set k, that's a feasible region. And the constraint is that this set k is defined by polynomial inequalities, which I denote here by h1 at least 0 up to hm at least 0, where h1 and hm are polynomials. So such a set k is closed. It's a basic closed semi-algebraic set. So we want to compute the minimum of p over this set k. And the characteristic of a polynomial optimization problem is that all the functions, the objective p and the constraints h, are all polynomials, multivariate polynomials. So this is the setting. So first of all, let us observe that such a problem is computationally hard already when dealing with seemingly simple sets k, which could be like the full space or the binary cube or the standard simplex or the hypercube or the sphere. So such sets seem relatively simple, but nevertheless, optimizing over them is already hard. And here are some examples just to illustrate this. So this is a combinatorial example. Suppose we have a sequence of numbers, A1 up to AN, integer numbers, and we want to decide whether one can partition the sequence, which means split it into two subsets, so that the sum of the AI over the first set S is equal to the sum of the AI over the complement of S. So you want to partition the sequence into two subsequences of equal sums. And this is a well-known NP-complete problem. And such a problem it's easy to model it as a polynomial optimization problem. What we could do, for instance, is try to minimize the sum of the xi ai square when restricting to the variables x1, xn being plus minus 1 valued. And then the minimum is equal to 0 precisely when the sequence can be partitioned. If you wish, you can also replace the constraints here that the xi should be plus minus 1 valued. You can incorporate them into the objective function by adding the sum of the squares of 1 minus xi squares here. Then we minimize this polynomial, which has degree 4, so it's a quartic polynomial, and we minimize it over the full space now. And the minimum again is 0 precisely when the sequence can be partitioned. So minimizing a degree 4 polynomial over the full space is already NP hard, because if one could solve it, one could decide whether a sequence can be partitioned, and this is an NP-complete problem. And as another example, coming again from a combinatorial problem, if we have a graph, so with such a graph parameter known as the stability number, which is the largest cardinality of an independent set, which can be formulated as such a polynomial optimization problem, where variables for the nodes, we are asking that xu, xv is equal to 0 for every edge, and that every variable is 0, 1 valued, and we want to maximize the sum of the variables. And this models computing the stability number, which is again an NP-hard problem. Another way to reformulate as a continuous polynomial optimization problem would be to minimizing a quartic polynomial over the standard simplex, which is known to again model the stability number. So minimizing a degree 2 polynomial over the standard simplex. So this is just a set of points which are non-negative, summing up to 1, the coordinate summing up to 1. So this is standard simplex. So nice, it's a little bit the simplest polyhedron you may think of, but minimizing a quadratic over this the standard simplex models an NP-hard problem. Okay, so polynomial optimization is hard. So then the common approach is to try to approximate this hard problem by designing easier relaxations for it. We are going to design a hierarchy of convex, in fact, semi-definite relaxations for it. And the crucial point is that these relaxations are constructed using sums of squares of polynomials as a proxy for positive polynomials. This is on the primal side, and on the dual side, we will have the theory of moments, which we already have heard several times in the preceding days about, but I will redefine what I need for the lecture. So this is this whole technology of approximating polynomial optimization using sums of squares and the dual theory of moments is about now 25 years old. It started with work by Shor, and then it was taken up by early work by Nesterov, Lasserre, Parillo from 2000, and the field has now a very broad literature. I will mention some books at the end of the lecture. So semi-definite programming will be a key tool. So I thought to include, probably unnecessary, but nevertheless, one slide reminder about what is semi-definite programming, just to have everybody on the same page. So probably what you all know is what is linear programming. Linear programming is optimizing a linear function over a polyhedron, and a polyhedron is a set of is a feasible region which is defined by equations, linear equations, and inequalities. And it can be, here is a standard form of LP. One would have only a linear equation, AJX equal to BJ, and the inequalities would be that the variable are requested to be non-negative. This is linear programming, optimizing a linear objective function over a feasible region, which is a polyhedron, which may look like this. In comparison, semi-definite programming will be optimizing a linear function over now a feasible region, which is a convex set, which is defined as a set of matrices. So one goes from vectors to matrices, capital X. Again, this matrix variable is supposed to satisfy a bunch of affine equation, aj dot x equal to bj, whereas here this is a trace-inner product. And while in LP, the variable is requested to be entry-wise non-negative, in SDP, the matrix variable is requested to be positive semi-definite. So the matrix is required to have non-negative eigenvalues. And so SDP would optimize a linear objective function over a feasible region, which may look like this. So now it's a convex, but non-polyhedral feasible region. And the key point is that such problems can be solved efficiently. So there are efficient algorithms to solve linear programming and semi-definite programming, with a caveat that for SDP, one should set some conditions on the program, like existence of a small ball or existence containing the feasible region and a big ball containing the feasible region. So there are some conditions. And one can solve the semi-definite program up to an arbitrary precision. So one picks a precision epsilon, and then in polynomial time one can find an epsilon approximate optimal solution. But roughly speaking, SDP is solvable efficiently. So here I've just recalled what is a trace inner product. So if we have two matrices C and X, so their inner product, the trace inner product is defined as a trace of C times X, which is just the sum of all variables Cij, Xij. So this is the usual Euclidean inner product. On viewing a matrix as a long vector, if you wish. So this is a typical shape of a semi-definite program in primal form. So optimize the objective function C dot X, subject to the matrix X should be positive semi-definite, so real symmetric positive semi-definite, and satisfying a bunch of affine equations. So every primal program comes with its dual. So we have affine equations, m of them. So we have a dual variable yj for each equation. So it's a dual variable as a yj, and the dual will ask to minimize the sum of the bj, yj, and the constraints will be that the sum of yj, aj minus c, so we take the linear combination of the matrix constraints aj and minus the objective matrix C, and we add that this matrix is positive semi-definite. So this is mimicking in a sense how the linear programming dual is constructed. And a very easy thing is to observe that there is weak duality. So the primal optimal value is at most the dual optimal value. This is basically relying on the fact that if we have two positive semi-definite matrices, if you take their inner product, then you get a non-negative number. And a very desirable property is to have strong duality, which means that you would like that the primal optimal is equal to the dual optimal, and this holds under some conditions, known as a Slater condition. The dual should be bounded and strictly feasible. So there are some conditions, so it's a little bit more technically involved in comparison to linear programming, but let's say that for all nicely set semi-definite programs, they will behave nicely and strong duality will hold. But it's just to indicate that one has to be a bit careful. Okay. So please, if there is any question, just don't hesitate to ask. Huh?
Questions? Yes, there is a question, Monique. Wait a second. Yes.
Yes.
Yeah.
For the prime definite program.
Maybe you can come here. Yeah, maybe you can come. Otherwise, I can reformulate it. But if it's a long question, I will answer.
Just
So come along here to the mic. That would be easier. Yeah.
I have the question about the prime of semidefinite program. Just for the matrices AJ, are they should be symmetric matrices, or it's not always the case? Because
Yes.
there are some papers that they don't mention that A is symmetric.
Yeah, so you are completely right. I should have written it. So in a semi-definite program, all matrices should be symmetric.
Okay.
Because this is how to say, if you would have a constraint which is AJ which is not symmetric, your variable X is symmetric. So if the constraint would be, for instance, just asking X12 is equal to 1, then you can as well rewrite it in a symmetric way by saying X12 plus X21 is equal to 2.
Yeah.
And
Okay.
the point is that the variable should be symmetric, so then you can as well assume as well that the matrices are symmetric. And you want to do that because if you look at the dual, then you are talking about positive semi-definiteness of a matrix here. And I want this to be also a symmetric matrix. So yes, everything should be symmetric.
Okay, thank you.
So in the real case, everything should be symmetric, and then you could also have, later we'll have also complex SDPs, and then the matrices should be Hermitian, complex Hermitian. Okay, thanks for the question. Yeah?
No, that's okay. Thanks, Monique. Go on.
Okay, so we go back to this is the setting of the polynomial optimization problem. We want to compute the minimum of P, denoted P min, on the set K. Well, first easy observation is that it's the same thing as finding the largest lambda for which P minus lambda takes only non-negative values when you evaluate this polynomial at a point in K. So P min is equal to the largest lambda for which P minus lambda is non-negative on K. This is an easy observation, but a useful one, because what we can do now, so testing non-negativity is hard because computing the minimum of a polynomial is hard. So this first line is hard, but then the idea is relax this hard line by something which might be easier, hopefully. And what we will now do is to look for sufficient conditions for P minus lambda to be non-negative. And what we do is we ask that P minus lambda can be written as follows. Can be written as a combination of the constraints, H1 up to Hm, where the multipliers, S1 up to Sm, are sums of squares. And we may also add an S0, which is the sum of squares. So we are looking now at the largest lambda for which P minus lambda admits such a conic decomposition where the multipliers are sums of squares. And let's call P source the largest such lambda. So then by construction, we get a bound which is a lower bound for the minimum, because if P minus lambda has such a decomposition, then P minus lambda is non-negative over K, and thus P source is at most P min. So this is obvious that this is a sufficient condition for non-negativity over K, because if we evaluate a sum of squares at the point X, we get a non-negative number. And if we evaluate one of the constraints at the point X in K, then we get a non-negative number. So we have, in this way, we have a low bound on the minimum that we call P source. So the rationale, why is this a good idea, maybe to look at this alternative bound P source, this alternative parameter. The rationale is that it is actually easier to test whether a polynomial P is a sum of squares of polynomials. So testing whether P is non-negative, this is hard, but testing whether P is a sum of squares of polynomials, this can be done efficiently using semi-definite programming. So let me maybe recall in one slide why is it easy to test whether a polynomial is a sum of squares? Why is it an easier task? So this is known as the Gram matrix method of Powers-Berman. So it is known since a long time. So here, let's look at the first line. We have our polynomial P, which we want to test to whether it's a sum of squares. So first of all, if P is a sum of squares, so I didn't write it, but it's written here. What does it mean P to be a sum of squares? It means that I can write it as a sum of squares of other polynomial QI. So the definition is just what the words say. So first of all, your P better have an even degree if it is to be a sum of squares, because if P is a sum of squares, it's non-negative, and it can only be non-negative everywhere if the degree is even. So this is why let's say that our polynomial P has degree 2D. So it's a sum of monomials where the P alpha is the coefficients and the X alpha is the monomials. And all the degrees are at most 2D. So we want to test whether there exist QI, polynomials QI of degree at most D, so that when you sum their squares, you get P. Okay, so here is something which is useful. Let us write our polynomial QI as the inner product of two vectors. One of them, which I wrote here, XD, is just the list of monomials up to degree D. You make a vector, and in this vector, you list the monomials X alpha up to degree D. And in the QI bar vector here, I just I make the coefficients of QI. If we look back, if you go back here at the definition of P, we see that this is the inner product between the vector of monomial and the vector of coefficients of P. So this is the only thing I do here. So now let's take up this line here, that P is the sum of QI square. I rewrite QI square in this form. So here is QI of X written as the vector of monomial in a product, the vector of coefficients. And here is the same number again, but putting first the vector of coefficients and second the vector of monomials. Now I pull out the vector of monomials on both sides. And inside I get the sum of QI bar transpose. So this red matrix here, it's a sum of rank 1 matrices. It's let's call X. It's a PSA matrix by construction. So what do we obtain? We obtain that P is a sum of square precisely when I can write it as the vector of monomial times X times the vector of monomial, where X is positive semidefinite. And here, this gives us a test how to test whether P is a sum of square. P is a sum of square if and only if one can find a semidefinite matrix X, which satisfies a bunch of equations. And what are these equations? These are just the equations that you get when you equate coefficients at both sides of this polynomial equation here. Here we have P of X, which is the sum of P alpha X alpha. And here we have another polynomial, which you could spell out. This would be the sum of X alpha X beta times X alpha beta. And you equate the coefficients here and the coefficients here. And you get this semi-definite program. So testing whether a polynomial is a sum of squares can be formulated as testing feasibility of an SDP. So maybe let's just work out an example. So do you see my little red bar? You are sharing screen on top, or maybe I'm the only one. Huh? So do you see well the heading of the slide?
We see the blue bar at the top.
Okay, good.
But we don't see any red bar.
Okay, very good. I see it. It's blocking my my polynomials, but it's okay.
So we see the polynomial very well.
Okay, so you see better than me. That's wait, move maybe. So sorry. I would like to.
Should I read the polynomial for you, Monique?
Yes, that will be very good. What is it? X4 plus?
X4 plus 2x cubed y plus 3x squared y squared plus 2xy cubed plus 2y to the fourth power.
Thank you very much, Didier. I should know this polynomial by heart, huh? But I
Yeah,
don't.
that's a classic.
So, okay, so here is our polynomial, two variables, degree 4, homogeneous of degree 4. And we want to test whether it's a sum of squares. So to make our life easier, since P is homogeneous, then we can as well search to write it as a sum of Qi square, where the Qi are homogeneous and of degree 2. So a Qi homogeneous of degree 2 is going to use the monomials x square, xy, y square. So this is the vector of monomials that is going to be used to write the Qi below the squares. And what we are looking for is this right matrix X here. So we want to find such an X PSD so that such an identity holds. So what we do, as I said, we equate coefficients on both sides. So let's look, for instance, the coefficient of X to the 4. In P, it is 1. And on the right-hand side, it's going to occur by doing x squared times x squared with a here. So the coefficient a should be equal to 1. Let's look, for instance, x cubed y. In P, it's going to be 2. And on the right-hand side, you get it by doing x. So it's b plus b, that's 2b. So it's x squared times xy or xy times x squared. And so on. So maybe let's do one more, x squared times y squared. So coefficient on P is 3. And how do we get it here? There are two ways to get it. Either you get it by taking xy times xy, since this is entry D, or you get it by doing x times, by doing x squared times y squared, which is C and C here. So the constraints will be 2C plus D is equal to 3, and so on. So you write all these constraints, and then you see that your matrix X can only be of this form. There is only one unknown, C is remaining, and you are looking for the C's which make such a matrix X PSD. And you can see that this is precisely when C is between -1 and 1. So there is a whole range of matrices X, which testifies that your polynomial is the sum of squares. So for instance, if C is equal to -1, you get P as the sum of 2 squares. And if C is equal to 0, which is inside, then you get P as the sum of 3 squares. So the number of squares in the decompositions will be equal to the rank of the matrix X coming up here. Okay, so I hope this clarifies that testing whether a polynomial is the sum of squares can be indeed tackled using semidefinite programming. So if there is any question?
Yes, there is a question, Monique.
Yes.
The sum of squares are just for homogeneous polynomials or
Are there sum of squares only for homogeneous polynomials or for arbitrary polynomials?
For arbitrary polynomials. Here I've chosen my P homogeneous just for the sake of simplicity, so that because I knew that the Qi would be homogeneous, and then there was less monomials to write here. Otherwise, if P was not homogeneous, you would set up a similar program, but then you would also use monomials of degree 1. So you would also put x, y, and 1. So you would put here the vector of monomials of degree at most 2. So you would have a longer vector with 6 monomials here, 6 monomials here, and here you would have a red matrix which should be of size 6. But you would do the same. You would equate coefficients on both sides. So the claim holds for an arbitrary polynomial, not only homogeneous. But in a sense, these two things are equivalent, huh? Because if you have a non-homogeneous polynomial, you can always homogenize by adding one more variable. But yeah?
Yes. No further questions, Monique. You can continue.
Okay, thank you. So now, okay, so we know how to test whether a polynomial is a sum of squares. So you may wonder whether all non-negative polynomial are sums of squares. Well, as you can guess, the answer is no. But let me recall this very classical result of Hilbert, which classifies precisely what are the pairs of number of variable n and degree d, for which the two notions of being non-negative over the full space is equivalent to being a sum of squares. And this is a very rare phenomenon that this equivalence holds. It holds in three cases. The first one is for univariate polynomials, n equal 1. So the claim is if a polynomial univariate is non-negative if and only if it's a sum of squares. The second case is degree 2. So a quadratic form is non-negative everywhere, precisely when it is a sum of squares. This corresponds to the fact, yeah, that's it. And the third exceptional case is two variables, degree 4. So in these three cases, being a sum of squares is equivalent to being non-negative. And in all other cases, there are non-negative polynomials that are not sums of squares. And here are some very classical results. So there is a famous Motzkin polynomial. It is a polynomial of degree 6 in two variables. It looks like this. It's given here. It is non-negative, but it is not a sum of squares. So I encourage you to do it for yourself to show this, that it's non-negative, but not a sum of squares. For non-negativity, you may use the arithmetic geometric mean inequality. And to check that it's not a sum of squares, you just try by brute force. And you look at coefficients and you come to a contradiction. The second classical example is three variables, degree 4. Again, an example which is non-negative but not a sum of squares. So these two pairs are the smallest pairs ND which do not fit in this pattern of three cases. And then any other pair, which for every other pair there is a polynomial which is non-negative but not a sum of squares, you can somehow build it using these two examples. Okay, so so this is discussing non-negativity over the full space versus being sums of squares. But what we are interested in also is about deciding non-negativity or positivity over a special semi-algebraic set K, which is defined by polynomial inequalities. And if you remember at the beginning, we said what we can do is look at the decomposition of P in this as a conic combination of the constraints with sum of square multipliers. So let's give a name to this set. This is a quadratic module Q of H generated by H1, Hm. So it's a set of all polynomials which have this form. This is a quadratic module. And clearly, if a polynomial is in the quadratic module, it is negative on the set K. And then you may wonder whether this is an equivalence. And this is almost an equivalence. So here is one of the results. So this result is due to Putinar. It goes also under the name of a positive Stellensatz, which is claiming the following. So assume our set K is compact, and there is the so-called Archimedean condition which holds, which I discussed after that. So assume K is compact plus a certain condition. Then the equivalence, the reverse inequality holds, but only when assuming that P is strictly positive on the set K. So if P is strictly positive on K, then P lies in the quadratic module. So we have this implication, and the reverse implication holds, assuming strict positivity. And what is the Archimedean condition? This is saying that with the equation of a ball, which lies in the quadratic module. This equation is not very difficult. This constraint is not difficult to be satisfied because we assume that the set K is compact. Hence, it is contained in some ball. So pick a ball containing the set K. So here is the equation of the ball. And what you do then, you just add this polynomial, non-negative, you add it to the description of your set K. So you add a redundant constraint to the set K and to the description of the set K. And in this way, you will get a polynomial description which satisfies the Archimedean condition. So this is one clear way how you may have this Archimedean condition be satisfied. So the point is that this Archimedean condition does not only depend on the set K, but it depends on its polynomial inequality description. And but for many other for many sets, it can be shown to be satisfied without adding explicitly the equation for ball. So, for instance, for the hypercube, it's satisfied. The Archimedean condition holds. For the simplex, it is satisfied. So it is a rather minor condition. So now that we have this theorem in hand, let us see how we can proceed to define a hierarchy of bounds that converge asymptotically to the minimum of P. So first of all, so maybe if we go back to the definition of the quadratic module, we see that this polynomial Sj are just constrained to be sums of squares. But if I want to have something which I can compute with, we should put a degree bound on the Sj. And this is the next thing to do. What we do now is we consider the truncated quadratic module. So we pick an integer t, and we call the truncated quadratic module at degree t, QHT. It's a set of all these polynomials where we assume that the Sj are sums of squares, but on top of that, every term has degree at most 2t. So you pick a degree bound and you restrict yourself to every term in this summation having degree at most 2t. So now we have a set which is living in a finite dimension of space, not in the full polynomial space, but in the space of polynomials of degree at most 2t. And then we define the SOS bound of order t as the largest lambda for which p minus lambda lies in the quadratic module, truncated at degree 2t. So maybe in this way, we find a lower bound, p sub t, on the minimum of p. And let's immediately look at the dual bound. So the primal bound, the sum of square bounds, is talking about polynomials. So the dual bound is going to be using as variables linear functionals L, which are acting on the polynomial space of degree at most 2t. So the variable here is a linear functional L, which takes a polynomial of degree 2t and brings it to a number. And L is linear. So the dual program to this sum of square program is going to be, you want to minimize L of p subject to L of 1 is 1, and now you just require that L should be non-negative on the truncated quadratic module. So we have seen several times yesterday linear functionals on rings of polynomials on truncated sets of polynomials. And the infimum we call, this is a moment bound of order t. And by weak duality, it's just by checking it. You take an L feasible here, a lambda feasible here, then you obtain that L of p is at least lambda. So the infimum, so the moment bound, is nested between the SOS bound and the minimum of p. And these are the, as we see in a second, both programs are in fact semi-definite programs, and they are dual of each other. So often we will have strong duality, so often we will have equality here, but at least we have weak duality. And the very nice property is that these parameters, so if you let t grow, you get a parameter which is better and better, which gets closer and closer to the minimum of p, and they converge asymptotically to the minimum of p. So in this way, we now have a way to achieve the minimum of p over the set k as a limit of parameters which are obtained as optimal values of semi-definite programs. And this asymptotic convergence follows using the positive standards of Putinaar, which I presented in the previous slide. So this holds under the Archimedean condition. So Any question about this?
Questions? No question at this stage, Monique.
Okay, thank you. So then I just want to now reflect a bit about the moment bound here. So as I just said, this is a dual of the SOS bound. These two are the two dual versions of. The moment bound is nested between the SOS bound and the minimum of P. And I want now to stress a bit some additional information that this moment bound may give us, because it gives more direct information on the minimizers of the polynomial. So let's step back a bit and understand again how this moment bound comes into the picture. So the basic idea is that, remember, you want to minimize P of X. P of X is sum of P alpha, X alpha. So X to the alpha is the troublemaker because this is nonlinear. This is a product of Xi. So this is nonlinear. And then the idea is you linearize this nonlinear term. And to linearize, you look at the linear functional acting on the polynomial up to degree 2t, and then you replace X to the alpha by L of X alpha. Maybe in the slides of yesterday by Bernard, it would be what would be called, it amounts to introducing a new variable Y alpha. So here I didn't introduce the names of the new variables. For me, the name of the new variable is L of X alpha. It's L evaluated at X alpha. If we have this linear functional, we can look at its, can make a matrix out of it, so-called moment matrix, or it's a Hankel type matrix. What we do is, it's denoted MT of L. It's indexed by monomials up to degree t, alpha and beta at most t, and the alpha beta entry is nothing but L evaluated at X alpha times X beta. So if you have an L, you can make this matrix. If you have, in addition, a polynomial H, you can make a localizing moment matrix. So it's, so you see here, it is a moment matrix of HL. In the notation of Bernard yesterday, there would be a star between the H and L. So it's, if you have a linear functional and a polynomial H, you can make a new linear functional HL, which maps a polynomial P to L of PH. It's exactly what's happening. So the moment matrix would be, have entry alpha beta would be L of X alpha, X beta times H. And here there is this small shifting of degrees because your L is known only up to degree 2t. So here you should restrict the degrees of alpha and beta in such a way that the degree of X alpha, X beta, H stays below t. This is the purpose of restricting here this, the size of alpha beta. The exact degrees are, the exact details are not very important. It's just to avoid overflow. But the crucial point now is that L is non-negative on sums of squares. So L is non-negative on a square F, can be expressed by, it's equivalent to asking that the matrix MT of L is positive semi-definite. No, I didn't write the proof, but this is an exercise which I let you do it. It's very easy. You just write your F as sum of F alpha X alpha, and you split. It is very easy. So testing whether L is non-negative on squares or on sums of squares is equivalent to testing whether its moment matrix is positive semi-definite. And in the same way, testing whether L of F square H is non-negative for all these degrees. This is if and only if this moment matrix here, the localizing moment matrix, is positive semi-definite. So in other words, what this lemma is telling us is that testing whether L is non-negative on the truncated quadratic module is equivalent to a bunch of positive semi-definite matrix constraints. So the moment bound can be expressed as a semi-definite program. So I have just written here the moment bound it can be rewritten in an explicit way as a semi-definite program, whereas the semi-definite matrix that should be positive, semi-definite arise from the moment matrix of L. But okay, let's now see why is this useful. And it's useful for the following reason. So let's call this parameter dk is the largest half degree of the constraints. And then if we restrict to the, if we look at the submatrix of the moment matrix indexed by monomials up to degree t minus dk, we get a principal submatrix, which is shown here. And there is this result which gives a sufficient condition for optimality of the moment bound. So it gives a stopping criterion. So the stopping criterion goes as follows. So let L be an optimal solution for the moment bound. We pick an L, which is optimal solution for this program, for this SDP. And let's assume that it's flat, which means that the rank of its moment matrix is equal to the rank of the smaller submatrix here. And let's call R this common rank. Then the conclusion is that the moment bound is actually equal to the minimum. And this is the first conclusion. And the second conclusion is that because of this rank condition here, this flatness condition, one can actually efficiently find the global minimizers, and R of them, and they can be found using the information contained in the moment matrix. So this is a very nice theorem because it gives a criterion that you can test numerically. You solve your SDP, you check if the solution is flat, if this rank condition holds, then you know that your bound is actually exact. It's equal to the minimum. It's not only a lower bound, it's actually equal. And on top of that, you can compute the global minimizers of the original polynomial optimization problem. So this shows that under flatness, the hierarchy of bounds has actually finite convergence. And if time allows, I will give you tomorrow a sketch of proof in the non-commutative setting. So this is, I think, one of the distinguishing features of the moment view on this hierarchy of bounds for polynomial optimization. It's the existence of this stopping criterion via the flatness condition. So yes, so maybe I'm getting a bit tight in time. So let me just here mention a few links with the moment problem. So the moment problem is deciding whether a linear functional admits a representing measure. So whether one can find a measure mu, so that L of f is given by integration of f with respect to this measure. This is a classical problem in functional analysis. A first result, which is good to remember, is that when T is finite, then, and if L has a representing measure, then actually this representing measure can always be chosen to be finite atomic. So that of Chekhanov. And a second fact is, so this is first an easy condition. If L has a representing measure supported on K, then it should be non-negative on the quadratic module. This is the easy direction. And the result, which is also due to Putinar, which is the pendant on the moment side of the sum of square representation result I showed before. So the result of Putinar says that if the set K is compact and if the Archimedean condition holds, then we have equivalence here. So any L, which is non-negative on the quadratic module, admits a representing measure. So this is the equivalent, in a sense, on the moment side of the positive standards I presented before. And to just round up with what I said before, if L is non-negative on the truncated quadratic module, and if it is flat, then we can conclude that it has a representing measure that is supported on K and is finite atomic. So this result here is the result which is underlying the stopping criterion which I presented in the previous slide for the polynomial optimization problem. Okay, maybe I flash quickly through a number of things. So there is a lot of things one could say about this hierarchy, that finite convergence holds generically. There is a lot of research, for instance, on the quality of the bounds, and one can exploit problem structure to design more economical hierarchies, so exploit sparsity, exploit symmetry, or exploit presence of equations. So I flash quickly because the slides are available, and here are a few books which are dealing with polynomial optimization. And there is a lot of literature on it, and I also mentioned the title of a book, which was a result of the previous ETN project, Poema, which also goes about this topic. So maybe if there is a question, some questions, it's a good moment, because the next thing I want to do is to move to quantum entanglement.
Time for questions on the moment of squares. No question? So Monique, there is no question in the room.
Okay, okay, very good. So then I move to an application of polynomial on the sphere to detecting quantum entanglement. So first of all, what is entanglement? So this is my 2-cent introduction to quantum entanglement. So So what a notion of entanglement is, I will just read what is written. It's a physical phenomenon of quantum systems, particle systems, which reveals the difference between quantum and classical mechanics. So what happens is that you have a big quantum system, which is composed by some subsystems, so say 2 quantum subsystems. And the point is that sometimes there are correlations which are taking place between the 2 subsystems, which cannot be explained by the laws of classical mechanics. Something is happening which cannot be explained, and this something is arising because of the existence of entanglement between the 2 separate quantum systems. And so these additional correlations which are taking place between physically separated quantum systems, which cannot be explained by the laws of classical mechanics. This is due to the fact that entanglement is taking place. And entanglement is used as a resource now in order to try to carry out in a more efficient way some computational tasks like quantum computation, quantum optimization, quantum cryptography, quantum communication, etc. You will hear, of course, more about real applications of quantum information by more experts the coming days. And one way, so quantum entanglement exists in nature, and what people do is to try to quantify entanglement by building mathematical model which enable to quantify entanglement. And this mathematical model, which I will discuss tomorrow, are non-local games, and they are associated Bell inequalities. So in a nutshell, a Bell inequality will be a linear inequality over a certain set of classical correlations, and then there will be a bigger set of correlations, just the quantum correlations. And if there is a difference between the Bell inequality on the classical set or the quantum set, then it shows existence of entanglement. But today, what I want to do is a very simple thing, in a sense, is to discuss quantum states and what is entanglement versus separability. And tomorrow we will see how these quantum states can be used to define so-called quantum correlations. Okay, so quantum system is modeled by the tensor product space. So usually it is, you have a first space, C to the dA, tensor C to the dB. So there are 2 subsystems. The first is the A system, the second is a B system. You could have more subsystems, m at least 2, but for simplicity, we just look at m equal 2. What is the state of a system? It's represented by a Hermitian positive linear map, rho, which is acting on the tensor space, on the tensor product. So rho is usually represents the state of the system. It's Hermitian positive semidefinite. So you may write it like this. So this is the set of Hermitian positive semidefinite matrices of size dA, the size of Hermitian PSD matrix of size dB, which is equivalent to isomorphic to the set of Hermitian positive semidefinite matrices of size dA dB. And usually the matrix is supposed to be normalized to have trace 1. It's also known as a density matrix. So the object of interest are Hermitian positive linear maps acting on a tensor product space. This is the important part, that it's acting on the tensor product of two spaces. The first example to build such a rho would be simply to take an X, which is Hermitian of size dA, a Y, which is Hermitian of size dB, and take the tensor product. Then rho is indeed, if X and Y are PSD, then rho is also PSD. So then such a rho is acting separately on both subsystems, on A, on B. It's also called with a local action. A rho comes only by directly looking at what's happening on A, what's happening on B. And such rho, you call them separable. So rho, this is now a very crucial definition. Rho is called separable if rho can be written as a convex combination of such tensor products of matrices. So if rho can be written as a convex combination of X tensor Y, where X is PSD acting on the first space, Y is PSD acting on the second space. And then there is always this normalization, but it's not the crucial part. Of course, if X is Hermitian PSD, you can write it as a sum of rank 1 matrices. So, and you can do the same for Y. So then you could as well say that rho is separable if it lies in the convex hole of all matrices of the form XX star, tensor product YY star, where X is in the first space, Y is in the second space. So now little x, little y are vectors, normalized of norm 1. So this is this capital set, SEP set, or if I want to distinguish what are the dimensions, I put a DIDB. This is a crucial set of separable states. And rho is called entangled if it does not lie in SEP, if it is not separable. And entangled states are going to be used to create quantum non-local correlations. So this is a crucial definition. Rho is separable if it is a convex combination of such matrices. Okay, let's see a first example, a pure state. So a pure state, by definition, it's a rho which has rank 1. So it can be written as psi star, where psi lies in the tensor product space. It's not very difficult to see that such a rho is separable if and only if psi is a product space, which means that psi is itself a tensor product of two vectors coming from the first space and the second one coming from the second space. And this is not so difficult because if rho is separable, it can be written as a sum of rank 1 matrices. But rho is already rank 1. So then it means that rho should be equal to one of the terms occurring in your sum of rank 1 matrices, which gives you directly that psi should be a product state. So this is an easy thing. So then we are left with trying to understand when is a vector psi in the tensor product here, when is it a product state? When can it be written as a tensor product of two vectors? And this can be checked using the singular value decomposition. So there is a algorithmic procedure for checking this, because such a psi, if it is a vector in the tensor product, you can as well view it as a matrix, DA, DB matrix, And then what you do is you apply the singular value decomposition to this matrix, and you get the so-called Schmidt decomposition. And one can check that psi is a product state if and only if this singular value decomposition gives just one r equal to 1. So there is an efficient way to test whether a vector psi is a product state, and as a consequence, whether when a pure state rho is separable. Okay, so at least one case when we can do it. But in general, we need more conditions for that. So necessary conditions for separability, which has been long known in the literature, is the so-called PPT, which stands for positive partial transpose. So remember, our rho is acting on a product, tensor product of two spaces. So it's indexed by pairs. Rho has indices. It's indexed by pairs, ij, where I is in dA, the first, and j is in dB. So this is a list of integers from 1 up to dA, 1 up to dB. And then one can do the so-called partial transpose, which is you don't transpose the full set of indices, but you just transpose part of it. So like the partial transpose with respect to the first register, which is denoted rho TA, would be that you flip only the first indices, I1 and I2. So yeah, I don't read it because it's going to be more confusing than anything else, but you see what's happening. So here I had first I1, I2, then here you have I2, I1. So you flip only the first indices, and the second one keep the position. This defines a new matrix, which is a partial transpose with respect to the first A register. In the same way, you can define the second partial transpose with respect to the B register, and then you would flip the second entries G1, G2. First, you flip them. And the point is that if we apply partial transpose to a separable matrix, if we apply the partial transpose to a separable matrix, we get a matrix which is positive semidefinite. Because if here is a typical shape of a separable matrix, XX transpose tensor YY star, and if you apply the partial transpose with respect to the first register, it simply means replacing X by its conjugate. So you replace XX star by X bar star, but you obtain again a tensor product of two positive semidefinite things, so it's again positive semidefinite. So the positive partial transpose, if you apply it to a matrix rho which is separable, then it should create a matrix which is positive semidefinite. So if rho is separable, then rho should be positive semidefinite, its partial transpose should be positive semidefinite. So with respect to the first A or with respect to the B, so if you have these two conditions, this also implies the second one. So you can put that condition or that one. It will be in the presence of rho PSD, these two conditions are in fact equivalent. So this is a very useful, necessary condition for separability. And in fact, it was shown that it is sufficient in the case when the two spaces have dimension dA plus dB at most 5. So if you have a rho, it lies in the separable set for the dimensions 2, 3, if and only if it is positive semidefinite and the partial transpose is positive semidefinite. So the set SEP has a nice semidefinite representation given by these two rather easy conditions, positive semidefiniteness of the partial transpose, in the case when the sum of the d's is the dimension is at most 5. But this nice thing stops immediately because Hamza Fazi has shown that if the sum of the dimension is at least 6, then the set SEP does not admit a semi-definite representation. So you could imagine that there will be stronger relaxations than just asking this positive semi-definite condition, but none of them is ever going to define exactly the SEP set in general. So maybe I will let you look at this slide as an exercise. So this was giving a vector which is not a product space, product state, and its corresponding pure state, rho, which is psi star, is not separable because the rho is positive semi-definite, but the partial transpose is not positive semi-definite. So maybe what we can only look here is an example of understanding how the partial transpose looks like. So this is taking the blue block and the green block, and it is just exchanging them. This is what happens when you switch the first indices. And this matrix is positive semi-definite, but this one is not positive semi-definite because of this sub-block here, which is not positive semi-definite. And here was another example of a matrix. This is a case where the 2 dimensions are equal to 3, and this is a rho which is positive semi-definite. So there is a parameter A, and the matrix here is positive semi-definite for any A strictly positive. If you do the partial transpose, which I encourage you to try at home, then you get a matrix which is also positive semi-definite for any A strictly positive. So the PPT condition holds for this rho for any A strictly positive. On the other hand, it is known that the rho is separable only when A is equal to 1. So this example shows indeed that the PPT condition is not sufficient for separability in the case dA plus dB equal to 6 already. So a fundamental question in quantum information is we are given a rho acting on the tensor product, decide whether it's separable or entangled. We have seen that this is easy if rho is pure or if the sum of the dimensions is at most 5. And in general, this has been shown to be an NP-hard problem. So we need some sufficient conditions, some conditions to test whether a state is separable. And for this, we have the so-called DPS hierarchy, which was introduced by Doherty, Parilos, Pedalieri. So we are going to see this hierarchy, which gives auto approximation for the set SEP. And on the dual side, this corresponds to having sufficient conditions for membership in the dual cone, which will be sufficient conditions for positivity of a certain Hermitian polynomial. And this is interesting because this yields entanglement witnesses for when the state is not separable. So let me introduce the DPS hierarchy. So here is a lemma, which is what we want to see is a bunch of necessary conditions for separability. So let's assume our rho is separable. So it's a convex combination of such objects. So let's just assume for simplicity that rho is just one such object. And let's see what can we do. What we can do is to extend rho. On the B side, we look at it, we pick an integer t, and let's call it state extension rho t, which is obtained by doing xx star, tensor product. And now what we do, we insert t copies of yy star. So we get a new state, rho t, which is acting on CDA times CDB tensor product t times. Let's see what this rho t satisfies. Clearly, it is positive. It's positive semi-definite. second thing which is rather clear is that by construction, you can, if you permute the T copies of the B registers, it's just always YY star. So there is a certain invariance property of the T copies of the B registers. So it's a bit clumsy to say, but if you look at the shape of this rho T, you see indeed that the T last copies here you can permute them and you still get the same. So this is what this equation here is saying, that there is an invariance property under permuting the last T B registers. Let's not look at the details, just try to understand the overall picture. And there is a third property, which is that we can take the partial transpose of some of the we have here a tensor product of things, and we can take the partial transpose of some of them. And if we do this, we still preserve positive semidefiniteness. This is what this condition is saying. We can maybe take the partial transpose on S of the copies of the B registers, and we still get something which is positive semidefinite. So again, here maybe the details are maybe a bit difficult to grasp so quickly, but essentially this is what it is. You just take a few of the registers here, and you take the partial transpose of them, and you still are positive semidefinite. So this is what this extended state satisfies, P1, P2, P3. And finally, what is a link with the original rho? The link, you get it by tracing out what we added. We have added T-1 copy of YY transpose, YY star. What we do is we trace them out, and we get back rho. So tracing out, so taking the trace, usually the trace of a matrix is just the sum of the diagonal entries. And this more general trace here is because we have a matrix rho T here, which has a block structure, and that this tracing out amounts to taking the sum of the blocks, of the suitably labeled blocks, but this is essentially what it is. And the suitably labeled blocks, here is the exact definition. But it's essentially this, and why we get back rho, it's because the vector y has norm 1. So this is why we get back the state rho. So now the DPS relaxation of order T consists of all the rho which have a state extension rho T satisfying these 4 properties. So it's a bit maybe difficult at first sight, but so we get in this way a hierarchy of relaxation. If we increase T, we get a set which contains SEP, which is smaller and smaller, and they form this hierarchy is complete in the sense that if you intersect all of them, you get back the set SEP. In other words, if rho is not in SEP, this can be detected because it doesn't lie in one of the relaxation codes. So we have a hierarchy of outer approximations, which is tighter and tighter, and the intersection gives you back SEP. And the description of DPST is by means of linear equations and positive semidefinite conditions. So this is an SDP set, HDPST. So maybe we don't look at this, and maybe just let me try to reconnect this DPST, so the DPS relaxation, which I've just introduced in terms of state extensions of a given rho, which is a bit unwieldy maybe, but let's maybe reformulate it in the terms of the moment language, which we maybe a bit better understand. It's just a reformulation at the end of the day. So what is a claim? A state rho belongs to the DPS relaxation of order T if and only if the following holds. So with a linear functional, so acting only on variables y's, yy, and its conjugate, And so this is a space of complex polynomials in variables y and y conjugate of degree at most 2t. The point now is that L takes its values not in scalars, but in Hermitian matrices of size d8. You can look at such a thing. What are the conditions of this L? You want that if you apply L to y star, you find again rho. And this will fit in sizes. Rho is dA dB, and L takes values in matrices of size dA. So this is why it fits. The second condition should be that the moment matrix should be positive semidefinite. So you have to define it a bit suitably, but let's not look at the details. So the moment matrix should be positive semidefinite. And the third condition is that your L should vanish on the ideal generated by the equation of the sphere. So this is saying 1 minus the norm of y squared is equal to 0. And this is capturing the fact that SEP is a convex whole of XX, where the vector x and vector y should be norm 1. But here we focus only on the y variable because we have only the state extension in the y direction. So this is a reformulation of what it means to be in the relaxation of order t. So it's a moment reformulation. And here is, in a nutshell, how you would show completeness. Suppose you have a row which lies in all the sets. You want to show that it's separable. So for each t, you have a certificate LT, this linear functional which satisfies the three properties. Because of the positivity and condition 2 and 3, you can show that the entries of LT are bounded. So there is a converging subsequence L. Now you get an L which acts on the full polynomial ring, y bar, with taking values in Hermitian matrices and satisfying 1, 2, 3 with t is infinity now. And now this is the analogous of a Putinar result, but for matrix valued linear functional. If you have an L which is positive, vanishes on the ideal of a variety, then L has a representing measure supported on the variety. So L has a representing measure supported on the variety, which is here the sphere of size dB. And L takes its values in Hermitian positive semidefinite matrices. So this is a matrix analog of Putinar. Putinar result on the sides, on the moment side. And finally, we're almost there, because now we are interested only in evaluating L at monomials of degree 2. And then we know that we may assume that mu is finite atomic. And if we spell out what it means, we are going to exactly find the representation of rho as we find this separable decomposition. So I over time, so this is my last sentence. So the only thing I want to mention is that this is exactly the same pattern as the usual proof in the scalar case, but now it is just with linear functional, which takes their values in matrices instead of scalars. And this shows the completeness of the separable code. And let me finish with this slide. On the dual side, we would have this would correspond to the polynomial, to the matrices whose polynomial is non-negative. And we have this result of Fong and Fuzzy, which characterizes this non-negativity of polynomials. But for the interest of time, I stop here, and I'm sorry I'm already over time with a few minutes. Thank you very, very much for the attention, and if you have questions, please do ask.
Thank you, Monique, but you still have time, actually. Yes,
my God.
Yeah, you still have until 10 and 20 minutes, so which is about approximately 15 more minutes.
Okay, I got confused. I was looking at 10. I got confused. Sorry. Okay,
Yeah.
so then we can step back. And we can step back, and then I step back and I ask if there are questions. So maybe we just go back to was the definition maybe of the SEP of the DPS hierarchy. Whether there was any question on the DPS hierarchy, maybe first.
Yes, let's take questions from the room. No question that I can see.
Yeah. Okay.
No. Bernard as well. One question.
Monique, so
Yes.
can you see the, like from a geometric point of view, this set as part of a Segre-Veronese variety?
This is what it is. Yes. Yes.
Some convex bulk here of.
It is exactly this, Bernard. Yeah. But except that with the twist now that you insist of having these two parts, the X and the Y part.
Yes, so it will be S2 of X and tensor, well, in S2 of X, tensor S2 of Y.
Exactly. Yes. Yes. And yeah.
I have a question regarding the semi-definite representability of SEP.
Yes.
So it's known that there are convex semi-algebraic sets which are not semi-definite representable. And however, we don't know of small size examples, small dimensional examples. So as far as I can remember, there is a dimension 15 example with a copositive cone, and there may be a slightly lower dimensional example due to Scheidler, but I don't remember the details of it. And my question is, could you imagine constructing low dimensional convex semi-algebraic sets which are not semi-definite representable using SEP?
So SEP is one of them, huh?
Yes, but what's the dimension of SEP? The smallest possible.
So that's 3, 3. So okay, so dimension would be 9 times 9, I think.
Okay.
I
over the complex numbers.
So the dimension over the So what is the dimension? So the dimension is the dimension of Hermitian matrices of size 3 times Hermitian matrices of size 3. So Hermitian matrices of size 9. This is the dimension.
Okay. So that's much higher than 15.
Yes, I guess so. Yes.
Okay.
So maybe some projections of it. Yeah, I would go back to the paper of Hamza. We probably said stuff about this. Yeah.
Okay. Thanks. There is another question. Yes.
Can you hear me?
Can you hear?
Yes.
Okay. Following the question of Bernard, if SEP is a Segre-Veronese variety, can we then not just in the same interpretation see everything that is not in SEP as at least the second secant variety of this, or is this? Can we see the DPS hierarchy as also making statements about whether the state lies in some secant variety?
I guess so. I mean, I think that the view, the explanation in terms of moments, which I gave in the next slides, is a little bit doing this, no? So maybe one thing I want to say before we move to this. So the DPS hierarchy here is defined as a state extension, and you only extend the state Y. But you could also extend the state X. You could do a state extension on both sides. And then the completeness of the DPS, I mean, you would rather a DPS type hierarchy, even tighter, but involving larger matrices, and the completeness would follow directly from the Putinar result. So it would be
Monique,
yes.
There is another question by Bernard.
So following
Yes.
your question, so can the test to set be done with the tensor decomposition and looking at positive weights? So I guess.
Sure. Yeah. It is, in the end of the day, your rho is you try to find a representing measure. That's all you are trying to do. Yes. Yes.
So,
you know your rho, you know certain moments, huh? Exactly moments from which are given here. Huh? Xi bar, yj bar. This is the moments you know, which are given by the entries of rho at these entries, and you try to check whether there is a representing measure which respects these given moments.
Thank you. No further questions. So you needed some time, Monique, if you want to see it.
Very good. So I have 10 minutes now. Huh?
A little bit less. Yes.
Okay, good.
Let's end at 20 past 10 and 20 minutes.
Yeah, it's good. It's good. So maybe I just slowly go back to, okay, we have seen the completeness of the DPS hierarchy. So the point is that this hierarchy was introduced in the quantum setting, and the tools for showing the completeness were completely different than the tools I know, at least.